Hello, welcome back to Lecture 3a of Quantum Computer Systems. In today's lecture, we're going to talk about quantum architecture and quantum memory. Specifically, we will use the properties of qubits that we learned from previous lectures and discuss how to build an architecture with those properties so that we can perform computation on them efficiently and scalably. And in particular, we're going to discuss the relationship between a classical host CPU with the quantum hardware, and also discuss what is quantum program look like. In addition, we'll look at also some common operations on quantum memory and talk about the unique quantum mechanic constraints on how we can or cannot do on quantum memory. So first off, how do we use the properties of a qubit to build an architecture for computation? Well, let's start with something we already know from previous lectures, namely the circuit model for computation. In that model, we say one way to realize a computation is to implement a set of qubits that stores the quantum information in superposition. And then we apply an array of gates. And we learned from last lecture that they need to be unitary transformations. And we also need to extract information out of the qubits by measurement. So some readout mechanism. And now computations becomes transformations of input qubits to output qubits. What's different from a classical circuit is that now the inputs can be in superposition of quantum states. So let's discuss what is the hardware support that's needed to implement this. This is also called the DiVincenzo criteria, named after David DiVincenzo. First, in terms of the quantum hardware, we need a well-defined qubit implemented in some technology. And we know today there are many promising candidates, such as superconducting circuits or electron or nucleus spins of an atom. Second, the hardware must be able to initialize the qubits in some well-defined state. We call that process the state preparation. So first criteria is the well-defined qubit, and the second criteria is well-defined and realizable initial state. Now this state can be something as easy as zero state tensored together, the all zero state. Third criteria is that the hardware should be able to perform elementary quantum gate, so gate transformations. To be able to perform arbitrary transformation, this array of gates must be what we call computationally universal. We will make the definition more rigorous in a few minutes. And the fourth criteria is qubit stability. Ideally, these qubits needs to be stable, at least for the duration of computation, so nothing unexpected happened to the qubits. And the fifth and final criteria is that the hardware needs to be able to perform accurate readout or measurement. Great, so now suppose we can do all of the 5 things that we mentioned above. Then we have built a quantum hardware. Okay, so that is the hardware support for a quantum computer. Now, what about its software support? For its system software, well, first we need to know how to manage qubits. We need to know which qubits has been used and which hasn't, etc. And second, we need an efficient description of the unitary transformation that we wanted on those qubits. You can think of it as a notion of quantum program. And third, we should be able to translate a program description of the unitary transformation to the native instructions or gate array that the hardware supports. So a process called quantum compiling. This includes the optimization of the sequences of gates, as well as the process for generating quantum machine code for the underlying hardware. And fourth, we need some support for fault tolerance so that errors in the program can be detected and corrected. Later in the second module of the course, we will be discussing in more detail about qubit management, giving language support for quantum computation, as well as the quantum compiling process. And then in the third module of the course, we'll be dealing with architecture in the presence of noise. So we'll be touching on the ideal of quantum error correction. Now, a relatively easy approach to implement those software supports is to let a host CPU be responsible for the software support. So in current design of quantum hardware, a critical component is the classical host computer. So in current design of a quantum architecture, we will use the host computer to write down a classical program description of the transformation U, and the CPU will be responsible for controlling or instructing the quantum hardware to perform its array or sequence of gates and measurements. And then finally, the measurement outcome from the quantum hardware will then be the feedback to the host computer for further processing. And this is the approach that many state-of-the-art quantum computer architecture take to let a host digital computer be responsible for all the software control. But it will also be very interesting to explore the possibility of using quantum hardware to implement maybe some of the software support on the right-hand side. For example, can we store the quantum program in qubits or quantum memory? Is it feasible or wise to use a quantum circuit to perform quantum compilation? Or can we find some implementation of qubits that itself is fault tolerant? For example, the topological quantum architecture. So for the remaining of this lecture, I think it will be very interesting to explore the different possibilities and debate about the advantages and disadvantages of implementing those supports. In particular, let's take a look at one of those, namely the program description of the transformation U. Now, after this fun exploration, we'll then transition into a discussion, a more systematic discussion of what is possible versus not possible on quantum memory. Okay, so now the overall goal of this exercise is to realize universal gate array U, or in other words, specify arbitrary transformation U. So just like classical program, we can store a description of the transformation U in classical memory. But it's also fun to think about whether it's possible to store information about the transformation in qubits, a quantum analog of the notion stored program computer. So let me break up this exercise into answering two questions. First one is, what is an efficient program description of U? For example, if you wanted to write down a transformation U on a host classical computer, then you would need an efficient classical description of U. Or if you wanted to store the information about the transformation U in qubits, then you would come up with a quantum description. Now I want to break up the exercise into answering two questions. The first is, what is an efficient program description of U? And second, where do we store this description for U? So for the classical case, for example, if you're looking at transformation on n classical bits, then you would have 2 to the n number of possible input states and 2 to the n possible outputs. So how many different functions are there that transforms n-bit inputs to n-bit outputs? Well, the number of functions on n bits is x to the y, which is 2 to the n raised to 2 to the n. And we can simplify it as this. So in principle, you could store every functions on n bits in log of that many number of bits, which is 2 to the n times n number of bits. So what about the quantum case? Well, if you have n number of qubits, then the possible unitary transformation is in fact infinite. For example, if n is 1, then possible unitary transformation on one qubit can be written as this in its most general form. Where we use 3 independent real numbers to specify, namely alpha, beta, and theta. And in general, for arbitrary m, U is parameterized by order of 2 to the 2m independent real numbers. Now I want to get back to our questions. Do we have an efficient program description of an arbitrary unitary transformation U, whether it's stored in bits or in qubits? Well, fortunately, the answer is yes for both cases, with some subtleties. And storing quantum program in classical memory requires that you have an efficient quantum compilation algorithm that decomposes the unitary transformation U in a sequence of universal instruction set. And storing quantum program in quantum memory means that you will need to prepare the qubits in some quantum state in the first place, and executing program stored in quantum memory will only succeed probabilistically. Well, we'll make these two statement or argument more rigorous. In the next few minutes, we will see for the classical case, what does it mean to have an efficient quantum compiling algorithm? And later in the next lecture, we'll be talking about gate teleportation, which is a technique that we'll need in order to store and execute quantum program from quantum memory. Okay, first, let's try to find an efficient way to write down arbitrary transformation U classically. We have argued that for transformation on m qubits, we will need the matrix representation of the transformation is of size 2 to the m by 2 to the m, so that's not efficient. Let's put it aside. Fortunately, we have this remarkable theorem. I'm writing down its colloquial form here, but you can find a more rigorous mathematical description in the textbook. The theorem says single qubit and 2 qubit gates are computationally universal. So what does it mean to have these gates being computational universal? It means the following. Arbitrary transformation U can be sort of decomposed into product of multiple transformations, where each step is a unitary transformation that acts on only 1 or 2 qubits at a time, and identity on the rest of the qubits, which means to describe an arbitrary transformation on m qubits for some large m, all you ever need to do is to write down a sequence of matrices of size 2 by 2 or 4 by 4. I'm not going to give the full proof here in this lecture, but the one-line proof sketch is that the rho of W sub I is to transform the ith column of the unitary U to the ith column of the identity. So a description of the unitary becomes a sequence of 1 and 2 qubit gates. Furthermore, these 1 and 2 qubit gates can be chosen from some fixed finite instruction set. And for example, a minimal instruction set for universality is the Hadamard gate, T gate, and CNOT gate, where the T gate is something we haven't seen, but it's essentially z rotation of pi over 4 angle. Now, some of you might have noticed there are one more issues with this. With the construction given by the proof of the theorem, we would need exponential number of 1 and 2 qubit gates. In particular, using the method in the proof sketch, we will need 2 to the m number of single or 2 qubit gates, which leads me to the notion of efficient quantum compiling. Which I'll just state here, that for some instruction set, only a small number of gates is sufficient to synthesize arbitrary unitary transformation. In other words, a sequence of only polynomial length. In the textbook, I have included a reasoning behind this statement, but I want to emphasize that in order to describe classically a arbitrary unitary transformation, we will need an efficient quantum compiling algorithm. And another thing I forgot to mention was that 1 and 2 qubit gates are also necessary for universality because 2 qubit gates are necessary to produce entanglement between qubits. Otherwise, the qubits wouldn't interact with each other. Great. Now, writing down arbitrary unitary transformation in qubits will be a bit more trickier. So we will leave that to the next lecture after we have introduced the concept of gate teleportation. Now, for the remaining time of the lecture, I'm going to discuss more systematically what are the operations we can do or cannot do on qubits, in other words, on quantum memory. Okay, so first let's start with some common operations on classical memory and see if we can implement the analogous version in quantum memory. So how do we load data from quantum memory? Well, as we learned from last lecture, this is accomplished by the process called measurement, which very importantly could disturb a quantum state. And the analog of the store operation is state preparation, which get the qubits into some specific states. Now, when we talk about logic on quantum memory, I want to distinguish two types of logic, namely classical logic from quantum logic. Yes, we can implement classical logic on quantum memory by applying its reversible version. For example, the operation of AND gate will be transformed to its where in the classical case, it's just our good old conditional branches instructions. Where if some conditions matches, then the instruction is executed. There's also a quantum conditional, in other words, controlled quantum gate, where the execution of a transformation U is conditioned on one of the qubit being in the state 1. Now for the rest of the lecture, I'm going to talk about two other slightly more complicated operation, namely move and swap. And you might ask about other operations on quantum memory, like how do I reset a qubit into some value? And how do we compare the state of two qubits? And even more, can we apply error correcting code with redundancy on qubits? I think that would be a fun exercise to do after the lecture, and I might put some of them in the homework. So let's get back to the two operations that we are going to talk about in the lecture, namely move, which involves copying or duplicating data and stored in qubits. And the second case for swap, it's about exchange data between two qubits or two systems of qubits. Okay, let's get to it. Can we make a operator, or can we make some transformation that would copy the state of a qubit into another, where you input psi and 0, and after transformation you will get two copies of the quantum state psi? Well, the answer is, unfortunately, this is not possible in general, or in other words, for arbitrary psi. Now here's the slightly more rigorous version of the theorem called no cloning theorem. There's no unitary that can transform all quantum state psi to two copies of psi, namely psi tensor product with psi. The reason is that if you were to transform a arbitrary quantum state, for example, for single qubit alpha 0 times beta 1, tensored with some other known state 0, and transform it to alpha 0 beta 1 tensored with alpha 0 beta 1, which is equal to alpha squared 0 0 plus alpha beta 0 1 beta alpha 1 0 plus beta squared 1 1. And notice that this transformation is not linear. So you wouldn't be able to find a unitary transformation, which is a linear transformation, from the left quantum state to the right quantum state. A more rigorous complete proof of the no-cloning theorem would require you to also rule out the possibility of doing so, even if you are allowed to produce some irrelevant garbage quantum state as output as well. But I want to make several important remarks here about the no-cloning theorem. First, it is possible to copy known state. I say copy, but in fact we are cheating here a little bit because we can just prepare multiple copies of the quantum state with some state preparation circuit repeatedly. For example, if we know the quantum state psi that we want to copy is the plus state, then if you have one copy of the plus state, we can just apply the state preparation circuit from 0 to plus to get two copies of the plus state. So second remarks is that it is also possible to copy within each of the bases. For example, if you have input state psi, which is alpha times 0 plus beta times 1, we can use the C0 operation to produce something that is alpha 0, 0 plus beta 1, 1. Notice that for each of the bases, we have accomplished something that resembles a duplication of data. And in fact, we have studied this in last lecture extensively. This is how we produce entanglement or entangled copies of quantum data. Now, finally, can we exchange quantum data between two qubits, for example? Can we accomplish this swap operation between quantum states psi 1 and psi 2? So after the transformation, we end up with psi 2 and psi 1. The answer is yes. Let's take a look at this quantum circuit consisting of 3 CNOT gates. Let's try to analyze what quantum state would come out of on the other side. Let's start with something simple. Suppose psi 1 and psi 2 is in a joint state, for example, 0, 0. After the 3 CNOT, what would the quantum state be? Well, we can work out the transformation of the CNOTs one by one. It gives 0, 0 back. Okay, what about the input state 0, 1 for the two qubits? Well, the first CNOT does not do anything because the first qubit is 0. The second CNOT does flip the first qubit because the second qubit is in 1. So after the second qubit is 1, 1. And then the third CNOT also does something. It flips the second qubit back to 0. So at the end of the day, you will get 1, 0. What if you pass 1, 0 in as input? Similarly, you will get 0, 1. What about 1, 1? Well, you will get 1, 1. So if you have an arbitrary quantum state, namely alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1, after the 3 CNOTs, you would transform each of the bases to the right-hand side where you have alpha, and then beta comes down here, gamma goes up here, and then delta stays here. And try to verify it yourself if you have some product state, psi 1 and psi 2. This is exactly what we wanted, namely psi 2 tensor psi 1 as output. And finally, this swapping operation also works for entangled quantum state, in which case the amplitudes on the bases 0, 1 and 1, 0 will be swapped. And for multi-qubit systems, chaining a sequence of swapping operations will give you a transformation that is equivalent to the permutation of the basis states.